Good morning. Let's go ahead and get this started. So I'm David Vossel. I'm one of the core contributors to the KubeVirt project. Today I'm joined with Vishesh Tanksale from NVIDIA, and what we're going to do is I'm going to jump into this by talking about KubeVirt, what it is, talk about the architecture a little bit. Then I'm going to hand it over to Vishesh, who's going to talk about how NVIDIA is leveraging KubeVirt for their GPU workloads. So to kick things off, I know this is a little bit backwards. I want to talk about what KubeVirt isn't. So inevitably, I get these questions after my presentations, and I just want to go through them right here in the beginning, and maybe it'll give someone who has these questions a better context of what we're doing by just knocking these out real quick. So first off, KubeVirt, it's not involved with declaratively managing your AWS or GCP or cloud virtual machines. We're talking about running KVM workloads on Kubernetes nodes. Next up, KubeVirt, it's not a competitor to something like Firecracker or Kata containers. We're not targeting this micro VM isolation use case at all. And last off, KubeVirt, it's not a container runtime. So we're going to work with whatever container runtime you guys are already using. And that's how we play nicely with things like the network service endpoints and persistent volume claims and things like that. All right, so what is KubeVirt then? This is my definition. KubeVirt is a Kubernetes extension that's going to allow us to run traditional virtual machines natively side by side with container workloads. And what I mean by traditional virtual machines is I'm talking about the same types of use cases you might have used AWS or GCP or even OpenStack for in the past. I'm talking about taking your traditional Windows and Linux virtual machines, bringing them into Kubernetes and managing them in a cloud-native way next to your container workloads. So when you're thinking about the kind of use cases you can solve with KubeVirt, we're in this space of solving the same kinds of things you might have done with public and on-premise cloud provider APIs in the past. Why would we do this? I mean, we already have things like OpenStack and Overt. We already have the public cloud. So why are we reinventing this virtual machine management stuff all over again? So KubeVirt, the initial motivation for it was this idea of infrastructure convergence. So what we saw as people were transitioning to the cloud-native, container-first way of doing things, it wasn't always a clean transition. So sometimes they were left with two stacks. They had one for the new container workloads, and they had an old legacy stack for their virtual machine workloads. Operationally, that's not great. So of course, with KubeVirt, we have one stack. So people can transition to their container workloads, bring their legacy VMs with them, and then we're going to reuse all the same logging metrics and monitoring, the same cluster networking, storage, things like that. And this use case is proved useful for people. We see people doing this in practice now. It's not theoretical at this point. And as time has gone by, we've actually seen some kind of new potential emerge for the project. So what's happening is the operational story around how Kubernetes is deployed, managed, and scaled, especially on bare metal, it's put KubeVirt kind of in the crosshairs of being considered for virtual machine-only use cases. So with addition of things like the cluster API and the machine API, what we have is Kubernetes managing its own underlying infrastructure. So Kubernetes, it's already super efficient at managing your workloads, but now it's becoming super efficient at managing the underlying infrastructure that those workloads run on. So when people are looking at places to run their virtual machines, and they want to leverage that kind of infrastructure management, KubeVirt makes a lot of sense for them. So it's becoming just a good place to run virtual machines standalone. And then there's also the operational management of the virtual machines themselves. So like today, you're using a declarative approach for managing your pod workloads. We're doing the same thing in KubeVirt. Kind of make this tangible to you. Here's an example everyone's familiar with of how to declare a pod. You post it to the cluster using standard kube control client tooling. Same thing with our virtual machine API. So point here is our virtual machine API, it maintains the same look and feel that you're looking for with Kubernetes, The main differences, of course, is our spec's going to have things related to virtual machines and not necessarily containers. So I know you aren't posting like 10,000 pods individually to your cluster. Instead, you're going to use something like a pod and a pod template and a deployment and scale horizontally that way. We want to maintain those same kind of patterns with KubeVirt. So you can take your virtual machine instance, put it in a virtual machine instance replica set, which just is another API that we support. And you can scale out using similar patterns that you are with pods using that API. So big takeaway here, manage your VMs like you manage your pods today. All right, that was a quick overview of what we're doing with KubeVirt. I want to kind of look under the hood now and talk about how we're doing this. So I made the statement earlier that KubeVirt is not a container runtime, and that we play nicely with things like network services and things like persistent volume claims. How are we doing this? We're doing this because we play by all the rules, because at the end of the day, KubeVirt is just running a QEMU process in a pod. That's really just about it. A little bit of feedback going on here. All right. Let's kill it. Good. All right, so it's a QEMU process in a pod. I don't want to trivialize the fact that there's a whole set of like APIs and cluster components that are involved with everything out to the point of launching that QEMU process in the pod, but at the end of the day, it's just a process in a pod. So to kind of demystify everything that's involved with bringing up that process, I'm going to go through the virtual machine launch flow. Starts with defining your virtual machine instance in a manifest. You use standard kubecontrol clients command to post that manifest to your cluster. That VM object's going to hit the API server. It's going to be persisted in etcd. And then what we have is a KubeVirt cluster controller called Virt controller, which is watching for your VM objects. It's going to be informed. There's a new virtual machine object's been posted to the cluster. And in response to that, it's going to create a pod for that virtual machine to live in. So this is the place where if you defined, for example, that you want a virtual machine with 2 cores and 8 gigabytes of memory, that you're going to have things translated from the virtual machine instance spec to that pod definition. So in that case, we would have resource request limits on the pod, reserving those resources. In the same sense, if you wanted to give your virtual machine dedicated GPU, which we're going to talk a lot about here in a second, you would define that on the virtual machine, which would be translated into a resource on the pod definition. So for controller, it's going to post that pod for the VM to live in. It's going to get scheduled using your standard Kubernetes scheduler. It's going to wind up on a host that has access to all the cluster resources you need. It's going to start up. And what we have here are 2 components that we need to talk about. Virt handler. It's a privileged daemon set that's going to exist on all compute hosts in your cluster. And Virt launcher, which is this tiny shim process that's only responsible for bringing up that QEMU process in the pod. So Virt launcher, it's a dumb process. It has no privileges except exactly what it needs to start that process, and has no access to things like the Kubernetes API server or anything like that. So the pod comes online. Virt launcher is the entry point. At that point, Virt handler is going to pass over all the arguments that are needed to start that QEMU process. So Virt launcher gets all the arguments it needs, starts up that QEMU process, and what we have is a virtual machine running in a pod. And at this point, that virtual machine has actually assumed the role of that pod. So if you ping that pod's IP address, you're actually going to get a response from the virtual machine guest, and it's going to see that it has that IP address. So what I want to do now is I kind of want to zoom in on that pod and talk about how we're delivering things like storage, network, and access to host resources. Starting with storage, if you want to give persistent storage to a pod, you're going to use a persistent volume claim. That's just how it's done. So a pod is going to be decoupled from the stateful storage with a persistent volume claim. We can use, since virtual machines are just processes in the pod, we can leverage these PVCs to deliver things like virtual machine images in a way that make them accessible to that QEMU process. So for example, if you have a virtual machine image on your laptop, you can upload that image using the containerized data importer, which is another project we're checking out. You can upload that to a PVC, and then we can attach that PVC to the virtual machine's pod and make that image that was just on your laptop accessible to a QEMU process, and we launch a VM with it. So end result here is we have virtual machines where we're delivering the virtual machine volumes using persistent volume claims. And if you stop and then start your virtual machine, we've decoupled the virtual machine process from those volumes. So if you make writes or do anything to your virtual machine, those changes will persist across multiple start-stop events. And with regards to networking, so in that pod, we have access to the CNI allocated network interfaces, and we can use that interface to tie the virtual machine directly into the pod network. So this is how we're playing nice with your network services and service endpoints and things like that. In addition to this, we support the ability to tie multiple CNI allocated network interfaces into your VM using Multis. So this is going to give you the flexibility to bring your VM, attach it to whatever network you want, or even multiple networks. And lastly, moving on, I want to talk about host resources. So again, we're just going to leverage existing features in Kubernetes to provide host resources to our virtual machine. CPU manager, that's how we're pinning virtual machines, underlying cores. All right, and then we also have topology manager, which is what we're leveraging to tie in NUMA affinity into all this, but that's a bit of a work in progress right now, both upstream in the Kubernetes community and us consuming that. With guest CPU, and with guest memory, we're doing something similar, so we can guarantee a certain amount of memory for our virtual machines by using pod requests and limits. And lastly, we can pass host devices into the pod's environment using device plugins. So this is how we're passing in things like GPUs, SRIOV, into that pod environment and ultimately onto the virtual machine. And the nice thing about device plugins is we can do this in a way that doesn't have to grant that pod elevated host privileges. It also ties back into the scheduler. So when you're requesting these resources on the pod, your pod's only going to get scheduled to a place that actually has these resources available. So there's some bookkeeping going on our behalf here. All right, flew through that. That's KubeVirt from like a 10,000-foot view. We might have time for questions, I don't know. I'm going to the the Red Hat booth after this, and I can answer KubeVirt questions or anything like that, or you can catch me afterwards. For now, I want to hand it off to Vishesh, who's going to go through the GPU use case that NVIDIA is looking at. And hopefully, you don't have feedback.
So thank you, David. And good morning, everyone. I'm Vishesh. I've been working at NVIDIA for last 1 year. So going back a bit, why are we talking about VMs in a Kubernetes conference? VMs are critical for us at NVIDIA because there's this big push to containerize GPU workloads, but not all GPU workloads can be containerized. Especially GPU workloads like gaming or professional graphics, you can't containerize them. You still need VMs for them. And that's why having containers and VMs together is kind of very critical for NVIDIA. And that's where we stumbled upon KubeVirt, which kind of helps us in that use case. But KubeVirt lacked one of the critical features which we require, that is assigning GPUs to the VMs. And that's when we decided to work on it, and we have recently upstreamed that change. So as David mentioned, to pass on and host resource to a KubeVirt VM, the natural choice is to have a device plugin, and that's why we developed this KubeVirt GPU device plugin, which is open source now. You can take a look at the details of it on the link below. So how does it look? Where does the GPU device plugin sit in the whole stack? So at the bottom, you can see there are these GPUs. You can either have a VFI or PCI driver attached to the GPUs. A VFI or PCI driver would allow user space process to have direct access to that GPU. Here, the user space process is a KubeVirt VM. If you want to split the GPU into multiple vGPUs, then instead of a VFI or PCI driver, you can have an NVIDIA vGPU manager. An NVIDIA vGPU manager would split your physical GPU into multiple vGPUs. And each of these vGPUs you can then pass on to your KubeVirt VM. NVIDIA vGPU manager creates mediated devices, and these mediated devices are passed on to the KubeVirt VM. On top of these drivers sits the device plugin, which we have developed. The device plugin kind of abstracts the details of the GPUs. It kind of understands the GPU topology on the host and exposes it out to Kubernetes. Kubernetes and KubeVirt together use these devices which are exposed at a device plugin, and as David kind of explained, it creates a KubeVirt pod. That KubeVirt pod has a KNU process in it, and that KNU process has the GPU, and it creates a VM. Going into a bit more details of what the device plugin does, so typical Kubernetes device plugin would have these 4 functions. First would be discovery. The device plugin discovers what all GPU, vGPU devices are there on the host. It then advertises it in a manner that your kubelet can understand. Once it does that, it waits for an allocation request from the kubelet. And in the meantime, it is also doing a health check on the devices which it has discovered. We'll go into the details of how it does this in the later slides. I think no KubeCon presentation is complete without some YAMLs. So here are my YAMLs for you. So once the device plugin comes up, it kind of exposes that, and it advertises those GPU devices to a kubelet. The node shows those GPU devices as allocatable devices. You can see that on the left, that there are 5 GPUs on that node. Once you have that, you can schedule a virtual machine instance which is requesting a GPU. And it will get automatically scheduled, not automatically, but the KubeVirt scheduler would kind of schedule it on the node which has these GPU devices. So the request for the GPU on the virtual machine instance kind of gets translated into an limit and request for the resources on the Virt launcher pod, and that Virt launcher pod is scheduled on the node, and then VM gets created. Now, going into a bit of details of how the device plugin actually does its discovery and advertisement to the kubelet. First, the device plugin, when the device plugin comes up, it reads what all PCI devices are there. Out of those, it filters out the NVIDIA GPU devices. Then it checks what kind of driver they have. If they have a VFI or PCI driver, it will group all the similar kind of GPUs together. It will also read if there are any mediated devices created by the vGPU manager, and it would group all of them together. Once it has identified all these devices, it will register itself. It will create a gRPC server, and it will register itself with the local kubelet on that host. And it will kind of advertise that, hey, I have this kind of device and these many number of them. Once the device plugin does this, it kind of waits for an allocation request from kubelet. In the background, it is also doing a health check on all of the resources that it has advertised to kubelet to ensure that these devices which it is kind of managing are healthy. Once it does that, then the device plugin, as I mentioned, is just waiting for an allocation request. Now, the allocation request would come in form of an creation of an KubeVirt VMI. So David kind of explained it a bit. I'm just going to gloss over it, that you pass on to the API server request to create a VMI. Since it is a CRD, it contacts the Virt controller. The Virt controller kind of translates that VMI spec into a pod spec, and a node is identified. And once a node is identified, that's when the device plugin again comes into the picture. Now, kubelet would realize that it is requesting a GPU device, and it knows that the GPU device is being served by the device plugin. So kubelet would contact the device plugin. This is what the allocation request is. So kubelet would contact the device plugin and ask for allocation of a resource. Once that request comes in, device plugin would decide which of the GPUs that it is available it would allocate. It would respond with an allocation response. This allocation response would be in form of an PCI address. The device plugin tells kubelet that this is the PCI address which I want to allocate, and you have what the mechanism we have used is we set an environment variable in the corresponding pod that would be created. So the kubelet would then create this pod. This pod would have an environment variable with the PCI address. Once the Virt launcher pod comes up, it reads this environment variable, it gets this PCI address, and when it reads this PCI address, it translates those details into a parameter into the libvirt DOM XML. So it reads this PCI address, translates it into a parameter into DOM XML, passes to the libvirt, and bang, libvirt creates a VM, and the VM has the GPU which has this PCI address. That's all that is to it, and now you have a KubeVirt VM which is running on a Kubernetes cluster, and it has a GPU assigned to it. You can maybe run your games on it. You can play your games on a Kubernetes cluster if you want. Going ahead, this is what the GPU pass-through is all about on KubeVirt. I just wanted to gloss over some of the use cases or some of the features of KubeVirt which we are using at NVIDIA. So we found that KubeVirt is really feature-rich. On the networking side, we are highly invested in using SRIV support and the multi support. That has been like a critical feature for us. On the storage side, we are using the PV-PVC model of storage, which kind of works really well for us. It's kind of consistent with what you give to a container, so it really works well for us. Another critical feature for us is the block PV support. We want to do disk pass-through to the KubeVirt VMs, and block PV support kind of becomes the critical feature which is there on Kubernetes, and KubeVirt also supports it, so we kind of get to do that pretty easily. The containerized data importer is also really important. For us, we use it heavily. It allows us to have immutable disk images. Another critical feature is the copy on write disk support. KubeVirt has some support for it. We are planning to modify it to be more consistent with our use case, and we'll try to talk to the community, and maybe we can upstream that as well. After that, some of the Kubernetes kind of constructs which are consistent with the KubeVirt VM make it really easy for us to have our deployment. Something like adding a service account to VM, or having node selectors, affinities, taints, and tolerations, which we use for making some of our scheduling decisions. That's really has been a godsend for us. And then there is the CloudNet support, because we're kind of trying to create a farm of VMs. The CloudNet support works really well. It's seamless. It's just the way it works in any other VM management platform. And lastly, there's this on Virt launcher pod, there is support to add a sidecar, and you can tinker with the libvirt parameters. We use it for some of our testing purposes or for trying out few features if we want, and we are also doing some stuff on it in our production for copy on write disk support. We also use virtctl utility. virtctl is a KubeVirt utility. It gives you, one of the features which we use of it is the VNC access to the VM, for debugging purposes, or if the VM kind of doesn't boot up or something like that, we use that a lot. And lastly, we use the GPU support which we have upstream. So the GPU support on KubeVirt VMs for passing through the GPUs as well as passing through vGPUs to KubeVirt VMs. So yeah, this is it for me. I would like to thank KubeVirt community for letting me present today, and thank you.
Questions? Do we have time for questions?
Yeah, we have time for questions. Yeah.
I saw that you can also use your manager to support vGPUs, right? So you have controls for setting up
So scheduling and the algorithms for,
GPU for whether best effort or equal sharing.
so
How do you, like, if there are two physical GPUs?
I think they want to give you a mic just a minute. Because I think this is being recorded, so maybe. Go ahead, I'll just repeat your question.
So if we have two physical GPUs and they can have multiple grid sizes, right? So how is it going to identify what vGPU has the frame buffer size that you want? Can you specify all those details as part of the parameters?
So what I think what he wants to ask is if you have different types of GPUs, how do you decide which GPU is perfect for your workload? Kind of, right? No?
If you have a physical GPU and its grids can be 2 GB, 4 GB, 8 GB, 16 GB, right?
Yeah, yeah.
And that is identified by one of the parameters
Yeah.
when I create a VM.
Yeah, yeah, yeah.
Using a over.
Yeah.
So now when I use KubeVirt to create a VM, how can I select?
You can't actually do that. What will happen is there's just one GPU that is just one GPU which is exposed as a device, and you can't really. It's just one. You want to answer?
So the vGPU scheduling policy is set for the host itself. So whatever GPU scheduling policy you have, that definite equal share of a fixture will be true for every pod that runs on that server. Independently of the number of GPUs, the GPU scheduling is per server, per vGPU manager, and so it drills down for every GPU in the host.
Yeah, that may be okay, but how will you determine what, like if I have two physical GPUs, and then
Let-
one of them
Let's take this. This is taking too long. Are there any other questions? Yeah, right here.
Yes, so I'm curious if anyone has attempted to use KubeVirt to manage multiple coordinated VMs. So like a good example might be if you wanted to run Slurm inside of Kubernetes, but I could imagine other cases.
Multiple virtual. I guess I didn't really quite understand the question.
So I see how I can use KubeVirt to deploy a single VM. Suppose I wanted to deploy multiple VMs with dependencies between them. Are you aware of anyone who's written an operator or similar to orchestrate the management of multiple VMs as a single service?
Oh, I see what you're saying. So the question is how to manage multiple VMs as a single service. You can certainly write your own custom operator to do something like that, just like you can with the pod. The only things that come out of the box with KubeVirt with multiple VM management would be we have a virtual machine replica set, which lets you do things at scale. But if you're wanting any sort of custom coordination between multiple virtual machines, you're going to have to coordinate that yourself. All right. Sure.
My question is around, can we use the vGPU manager to essentially have these virtual GPUs presented in pods instead of using KubeVirt? So for example, we have use cases for AI jobs, and at this point we don't want to run them on VMs because the gaming is not the use case. So we want to be able to virtualize GPUs and essentially maximize our time on those GPUs because they tend to sit idle. Can that vGPU manager simply, along with the NVIDIA device plugin to Kubernetes, be used in combination without KubeVirt?
Is it standalone or is it integrated?
We have not tried it out. We have just tried it with the KubeVirt there. Currently, the thing is, if you want to have a container having a GPU, then there's a different device plugin for it. That
I was wondering if you already use that. I was wondering if you can use that to present the physical GPUs as virtual GPUs through that plugin. And then
I think we can discuss it later on. There is some possibility there.
It's possible, but so the question was if we can reuse the mechanism we're using for KubeVirt to expose the GPUs standalone for container workloads. And we'll talk about that afterwards. I don't think that's been done yet. Yeah.
Can I run a Windows VM?
Yeah, you can run a Windows VM. That was the question.
Yeah.
Yes.
Yeah, that's the whole purpose, I think. We need Windows gaming VMs, and they are one of our critical workloads, so they work all fine.
Yeah.
NVLink, are NVLink GPUs able to be presented?
In VLink?
So you're talking about understanding the topology of the. So the thing is, you can the whole issue here is, we need some amount of support from Kubernetes to kind of the topology manager kind of needs to support that. Once it happens, then we can kind of do the NUMA support on KubeVirt. So KubeVirt doesn't currently have the whole NUMA support. So once we have that, then it can translate into the KubeVirt VMs kind of understanding that and you scheduling stuff based on.
Is there a SIG around that yet, or do we have to create that?
There is some discussion going on around it that I know about.
You want to pick one?
So that from the health monitoring failure detection, the current situation, I was wondering, like for the KubeVirt, the support infrastructure for a VM application inside the virtual machine has any problem with pass back between the KubeVirt and outside Kubernetes world, right? Did you get the question? So basically, you run your application inside the virtual machine. You have a KubeVirt, tuning, right? And now you have your board outside. So what I'm trying to say, the health recover all those monitoring for all this stuff. We have the KubeVirt support in place, or customer has to provide the own mechanism in the virtual machine application outside the virtual machine.
So you want to say there's an application running on your KubeVirt VM and you want to monitor it and check if that application is healthy or something of that sort, or?
Yeah, because right now you're just running VM.
Uh-huh.
VM step doesn't mean some guy running inside of it.
Yeah. So you can obviously have some kind of a monitoring, maybe a monitoring pod that runs on that same cluster, which kind of does a health check, because the VM definitely has the access to all the components of the cluster. So if you want to have something of that sort, then that's possible. Or the application inside the VM can also, kind of send its status out to the outside world, where you have some application which is monitoring it. I don't see.
Yeah, I know the mechanism they have is quite there. I just want from infrastructure perspective. Now, because the Kubernetes is provider has proper radius proper for pod, right? Whether that will extend to the VM running the application.
So we have observability into the virtual machine. We're exporting certain metrics using Prometheus, so you can scrape metrics that are specific to that virtual machine. They're pretty standard stuff, like the amount of CPU used and things like that. And we're thinking about extending that to add guest support, so you could learn about when your virtual machine, the actual guest, has booted up completely and things like that. So I'm not sure that's the question exactly, but talk to us afterwards. All right, right here.
Yeah, hold on. I think it still sounds very similar to Kafka product. I mean, the way it works.
Yeah, sure. We're just not targeting, so the question was, we're similar to Kata containers. Do you want me to speak on that, or do you have more?
Maybe you can speak of some difference about, I mean, still similar to me.
Yeah, we're using KVM, just like that, but we're not targeting this micro VM use case simply because our API isn't optimized for that. We're creating an API that looks and feels like something you might use for traditional virtual machines in the past, and it's not meant just to be this tiny, slimmed-down thing that runs your container workloads. It's meant to run full-fledged, like Windows and Linux virtual machines. So, I mean, it does provide the same kind of isolation that you're talking about, simply because their hypervisor is involved, but we're not, I mean, you could use it for isolation if you wanted, but that's not what we're really going for.
The difference is the Kata probably is a clean version of the VM, and that you are going to provide a full VM.
Right, exactly.
Let's pick up someone from the back.
Somebody new.
Someone from the back, I think.
Oh yeah, somebody from the, all right, this guy.
Is there or will there be support for input device and monitor pass-through at any point?
Ooh. Import input devices and monitor pass-through.
So, you can, kind of do a sidecar and do hacks around it. That's possible, but there's no current support on KubeVirt
Yeah.
to kind of do it like from the KubeVirt API, kind of have a whole you need to build that around.
All right, one last question, and then we gotta go right here.
Assuming NVIDIA main manager works on a non-KubeVirt environment as well, how does this schedule CPUs as well in addition to GPUs? So let's say I have a Tesla 800 GPU, a 4 GPU machine that has 16 CPUs, and I want to divide that into different virtual cores. So how do I allocate CPUs to those virtual cores? Is there a combination that can work here?
So there, you mean kind of a NUMA support that you want to have the vGPUs as well as your CPUs from the one side of the NUMA or something of that sort? Or, so that is correct. That's I think I answered a similar question before. So that currently is not there on KubeVirt. We kind of need a bit of support from Kubernetes topology manager, and then we kind of have to pass on to, once you have that support, then KubeVirt kind of absorbs it, and then we will be able to do it for KubeVirt.
Suppose you have a 4 GPU machine and you are dividing it into multiple cores. So let's say for each GPU you are dividing it into 4 different virtual cores. So how do you allocate CPUs currently to that?
So it's at random, basically. There's no.
You're not going to have the affinity of getting as close as possible to
Yeah.
those PCI addresses right now. That's what Topology Manager is trying to solve, specifically for NUMA, but also we're looking at PCI devices like SRIVO and GPUs as well, where you want your CPUs that you're allocating, the dedicated CPUs, to be as close as possible to those devices. Just doesn't, we're working on it. It's something that Kubernetes is working on, and then we'll consume it when it's ready.
So by random, do you mean that there should be one CPU at the max 16 CPUs that will be taken up by a certain core if a process wants it?
Yeah.
All right, thanks.
Thank you.
Appreciate it.